Still doing quantum mechanics videos, and I'm going to show you how to solve for the radial part of the wave function for the hydrogen atom. And there's a lot of complicated stuff here, but let me just show you, this is what we want to get to right here. And we're not going to make this actual code, but you'll get the idea. So this is the radial part of the hydrogen atom wave function, and I'm solving it the shooting method. So in this case, what I'm doing is I'm changing the energy until I get this meeting the boundary conditions, and you'll see that little flip down there. That's what I was looking for. So that's what we're going to build. We're going to build this. Now, let's get started. Oh, and this is another solution. This is just a plot, so you can zoom in, it looks a little bit better. We're going to make that. We're all going to make that. Okay, so here is the hydrogen atom. We have a proton, an electron, separated by a distance r. We're going to assume the proton's stationary. Now, that's not true, right? And you can easily compensate for this. You can turn a two-body problem into equivalent one-bodied problem. You can use the reduced mass. I'm just not going to do it because I don't really care. Okay, it's not that big of a deal. You can change that later. We're assuming the Coulomb potential. So that the Coulomb potential, I'm using V instead of U. I don't know why. A lot of the books use V. I've asked some other people, and they're like, oh, it's V. We use V. And I don't know. So, okay. So V is the potential energy. And we have 1 over 4 pi epsilon naught. That's that Coulomb constant. Q1, Q2 over R. And then I'm just going to write this like this. So this is plus E. This is minus E. So plus E times minus E is minus. And then 1 over 4 pi epsilon naught is K. So we get minus K E squared over R. Now for the Schrödinger equation. So this is the most basic form. I h bar, the partial of psi, the wave function, with the Hamiltonian operator on psi is equal to the Hamiltonian operator on psi. And the Hamiltonian is like kinetic energy plus potential. Kinetic energy is p squared over 2m, and p squared is p is an operator. So we operate that twice, and we get a second derivative, which is in 3 dimensions. We're going to write as the Laplacian. We also get that h bar. Negative h bar because there's an I in there. And so that's the Laplacian Cartesian coordinates, which we're not going to use, but I just want to show it to you so it's easy to write. So that makes our Schrödinger equation look like this. That's our Schrödinger equation, okay? The derivative with respect to time of that, and this is the space derivative, and that's our potential. If we are using a point that we can describe the potential by a function of r, then it doesn't make sense to use Cartesian coordinates because then our potential is going to depend on x, y, and z, and that's going to make it very difficult. Instead, we want to use spherical coordinates. So I made this in Python. It's not the best, but you can see here we have the x-axis. Here's the y-axis going that way, and the z-axis, and a point r. We have the 3 coordinates for that r, the distance from the origin to the location. And then we have theta, and that's an important point, right? Theta is the angle from the z-axis. Now, sometimes, and then phi is the angle projected into the xy plane from the x-axis. Be careful. Sometimes they flip that. Depends on who does it, right? Typically, math, from my experience, math likes to put phi right there and theta down there. Physics likes to put phi down here and theta right there. And then I don't know why. It's just one of those things you got to accept. So you can probably figure out which way it is just by looking at the problem. So it's not a big deal. This light's kind of bothering me. Okay. Is that better? Let's get started. If I have spherical coordinates, I have to have the Laplacian in spherical coordinates. So the Laplacian spherical coordinates looks like this. So you're like, hey, I don't know if we're gaining anything, right? Yes, our potential only depends on r, but look at the Laplacian. It's a beast. Well, yeah, it is. Okay, but don't worry. We're going to be okay. We're going to take it slow. And the first thing we're going to do, and this has nothing to do with the hydrogen atom. This is true for most of the quantum mechanics problems you do. I'm going to assume the wave function has a space part right here of psi of r, theta, and phi, and a time part f of t. If I put this into my Schrödinger equation right here, I'm only going to have, I'm going to take the partial with respect to time. Well, there's no time in the space part. Here I'm going to take the partial with respect to space, and there's no space in that time part. So we can pull those out. And when we do that, we get Oh, that's that same equation. When I pull them out, so I'm going to pull out the psi right here. I'm going to pull out the f right there, and I'm left with this equation. Now, the trick is to multiply both sides by 1 over psi f, and when I do that, notice that psi f cancels here, the f cancels, and the psi cancels, and I get this equation. And it's really important, right? Because this part right here only depends on time. There's no other thing in there. It's only time. No space, no space. And this only depends on space. So if I have two sides of the equation, one side only depends on space, one side only depends on time, the only way that differential equation could still be true is if they're both equal to a constant, right? Because imagine I change time. Well, that would change stuff over here, but it wouldn't change stuff over here because there's no time. So this has to be equal to a constant because that's not going to change. And the same thing's true here. I change space, but time doesn't change, so they both have to be equal to a constant. And what do we call that constant? We call that constant E. So this right here is equal to E, and this right here is equal to E. So we have two equations. And what we're going to do is to solve those two equations. Those are our two equations. And, I think it's important to go back through and do this multiple times because I remember as an undergraduate that, we did it once and we're like, oh yeah, I remember that. But I forgot. I never remembered. Now, there is one very important point here that I like to point out. This does not always work. You cannot always do this. If V depends on time, not going to work. You can't do that. Okay, so we're only dealing with time-independent potentials. Okay, got it. So let's solve the time part. It's really not hard. Here is our function, right? We have the partial of f with respect to t is equal to e, and then we have that 1 over f. So we can multiply both sides by f over I, h bar, and we get this. Now, again, I didn't show you this, right? But if I divide by I h bar, I put the I up here and multiply by negative, because what I do is multiply by I over I, and then I get -1 on the bottom, and then I get the I. So that just moves the I up top, but I get a negative sign. Just don't forget about that. So this says, what function do I take the derivative of with respect to t and get the same function back? Well, an exponential would work. So we have e to the negative et over h bar would indeed be that function, and that is our time. And we're not going to do anything else with that, but I wanted to point it out every chance I get because we forget. Now let's go to our space function. There's our space function. We're going to assume actually that the space function is also a combination of a product of two functions. A function that only depends on r and a function that depends on theta and phi. And if I put that function into my Laplacian ry, I'm going to take the Laplacian of ry, you see what happens is that this first term only depends on r, so I can pull y all the way out the front. This term depends on theta, only theta, so I can pull the r out, right? The partial of ry with respect to theta, r doesn't depend on theta, so it comes out. And then over here, this term only depends on phi and theta, but if the derivative only depends on phi, I can pull the r out again. And then if I put this in the Schrödinger equation, I get this thing. And it looks messy, but just calm down. It's important to go through and do this yourself on hand on paper, and I would do it, but I don't want the video to take too long, and I don't want to make a mistake. So I put it here. I'm sorry. Okay. So here is this whole thing is a Laplacian up there, and then I had that negative h bar squared over 2m. Then we have v ry equals e ry, right? That's the same thing. That's v psi e psi. Now let's multiply both sides of the equation, that's what these yellow brackets are, by this term. And so when we do that, this term's going to go away for all the Laplacian stuff, but we're going to get it on these two terms. And notice down here I have ry. So right here, the y is going to cancel, the r is going to cancel, the r is going to cancel. Also notice that I have the variable r squared, because there's an r squared term right here, and I don't want those, right? You know where I'm going with this, right? You know where I'm going with this. So this term just becomes v, then I do have to multiply by the r, the negative m r squared, h bar squared, and same thing with that. But this term, the y will cancel, r cancels, r squared cancels, r squared cancels over there too, technically. Okay, so here is what we're left with. Doing a little bit of algebra, I saved you some of the hassle. I pulled that v term over to the other side, the e term to the other side, so combine those two together. And the important thing is that this stuff only depends on r. This stuff only depends on y, theta and phi. And so again, how can that be true unless they're both equal to a constant, right? If I change r and that doesn't change, it can't add up to 0. There's no way. So this has to be equal to a constant, and this has to be equal to a constant. And we call that constant L times L plus 1. And you're like, that doesn't make any sense. Okay, this is one of those things where it doesn't make any sense until you finish the problem and you see, oh, well, now I know why. Okay, so just don't worry about it. It's a constant, and that constant just happens to be L times L plus 1. Got it? And then so if this is L times L plus 1, then this is negative L times L plus 1, so that they add together and equal 0. This equation down here is really complicated to solve. It depends on theta, phi, and the solutions to this are the spherical harmonics. And I'm not going to play with that today. We're just going to do the radial part of the equation because I want this video to be completable. So this is our radial part of the equation. And notice that we only have the function r, and it only depends on r. There's no other terms. There's no theta, there's no y, there's no phi. So that's great. So we can work with this. It's a differential equation that we can work with. The first thing I'm going to do is multiply both sides by r, and that gets rid of this term right here. When I do that, I get this. So I just multiplied by r. This term comes down here. This term has an extra r in there, and that term has an extra r, and that's right there. Now, I want to solve this differential equation, but here I have a derivative of a product. So I need to just go ahead and take that derivative, even though I can't fully do it. But it is a product rule, right? So if I take the partial with respect to r of this term, I can take that term. I can take the partial of this with respect to r times this. So I get the partial of r with respect to r of r squared. It's going to be 2r, right? That derivative of r squared is 2r. And then I multiply it by this. And then I have to add in this term times the derivative of the partial of r with respect to r. And I'm saying capital R, if you can hear. That says capital R. R. See that? The derivative of r with respect to r. Capital, lower. Capital, lower. This is why I write. That's why I can do pictures too. So that gives me that term right there. So I can take this derivative and make it that sum. And then I have, putting in the rest of the stuff, I get this equation right there. Okay, so I have a first partial, I have a second partial, I have a term, and v does depend on r, and there's lowercase r, and then there's that term right there. So here's that equation. Now what I want to do is to solve this equation for the second derivative. So I'm going to move this term to the other side, move that to the other side, and then divide by r squared, and I get this. Is that okay? Okay, what am I going to do next? I'm going to plug in for this v. Remember, v is negative k e squared over r, right there. So that's important. So it's got a box. Everything that's really important has a box, but that you probably knew that one already. If I put that in for my potential, I get this. So this term's right here. The only thing different is that v became this term. What I did also was I factored out a negative sign. You don't have to, but I did. Since e and v, there's a negative sign right there. Factor that out, and you get that. And then that term's that term's that, and we're all happy. And that is the equation that we want to solve right there. Okay. Now, we do have a boundary condition. We have to apply a boundary condition, and this would make this problem hard, right? I can't just solve this differential equation. I have to solve it and say r at infinity is 0, because the wave function shouldn't, this is part of the probability distribution, right? And saying I can't have that electron an infinite distance away. The probability of finding if it's part of that hydrogen atom would have to be 0. That's how we're going to do that. Okay, so here is that same equation. And what I'm going to do is just to make it look a little bit simpler, I'm going to call the second partial of r with respect to r double prime, and I'm going to call the partial of r with respect to r prime, just so we can write it a little bit nicer, and it looks like this. Okay, so it's the same equation. I just have r double prime, r prime. Got it. Okay, now how do you solve a differential equation like this? This is where we're going to use the shooting method. To solve the shooting method, to explain the shooting method, I'm going to go back, and I have a whole video on this, I'll post it down below, to show you the shooting method in the 1D infinite square well, because we know the solution there. And I'm going to show you how that works, and then we're going to apply that for the hydrogen atom. So this is the shooting method for the infinite square well. What we do is, there should be a video. There it goes. So it's called the shooting method because we're going to solve for the differential equation and keep changing the properties of something, the energy, until we meet the boundary condition. So we're going to keep resolving the problem until it meets that boundary condition right there. I'm going to show you exactly how to do this. Okay, so there's our Schrödinger equation, and we're in one dimension. We're just in the x direction, and we only have we're going from 0 to 1. Right, that was my well, in case you didn't see that. So I'm just changing the Laplacian. I only have the derivative with respect to x, and psi only depends on x, so I can write it as a full derivative. Also, inside the infinite square well, the potential is 0, so that term's 0. And then again, I'm going to say psi double prime is the second derivative, and I get this equation right here. And this is the equation that we want to solve, right? That's the equation we want to solve. What did I just do there? Oh, okay, I just divided by this over here. So I get psi double prime is equal to that. How do we solve this equation? That's what we do. And we have the boundary conditions right here. And so we can start at x equals 0 and then model it until we get to x equals 1 and then see if we get psi of 1 is equal to 0. And if we do, that's a good solution. And that's why it's called a shooting method. Okay, so here's our Schrödinger equation. What we're going to do in the shooting method is break this into finite elements. We're going to go step sizes of, let's say, 0.01. And during each one of those steps, we have to use numbers here. Okay, we're using numbers. During each one of those steps, we're going to assume psi double prime is constant. We're going to assume the second derivative is constant. I know it's not, but we're going to assume it. Okay, that's fine. And so if we do that, I can write the second derivative of psi as the change in psi prime with respect to x, delta psi prime delta x. Now let's say that I call psi prime at the beginning of this interval right here as psi 1 prime, and at the end it's psi 2 prime, then I can write it like that. So that's the derivative at the beginning, that's the derivative then. It's just a difference. It's just like finding the slope. If I do that, I can solve this for psi 2 prime. Multiply both sides by delta x, add psi 1 prime, and you get that. Okay, this is important. This is our derivative update formula. And now we're going to assume that psi 2 prime is constant. The derivative at the end is constant. I know, we just changed it. I know that. But we're going to do it anyway. It will be okay. So if psi 2 prime is constant, I can write that as a difference of psi with respect to x, delta psi delta x. And again, that's psi 2, the wave function at the end of delta x, and psi 1 at the beginning. Again, solve for psi 2, I get that. That's my wave function update method. And so you can see we can take the values. If I know the value of psi and psi prime, and I can calculate psi double prime, which I can, then I can find the next one, and then I can do it again and again and again. This is it has several names, but this is basically the Euler method of numerical calculations. It's super powerful, it's super easy to implement, and that's why we're going to use it. Okay, so here's the recipe. If you were getting a cookbook and you wanted to write your recipe, it would look like this. Number 1, break the problem into small pieces, delta x. Number 2, we need to have starting values of psi. We know psi 1, we know it starts at 0. That's one of our boundary conditions. Psi 1 prime, we don't know. I don't know the derivative, so I just pick 1. I don't know the energy, so I pick 0. Then I can use my Schrödinger equation to calculate psi double prime. That's just my differential equation. I calculate that value. I can use that value to update psi prime. I can use psi prime to update psi. And then I can check and see if the boundary conditions are met. Psi 1 equals 0. If not, change my value of E and start over and do it again. That's the shooting method. If you want to look at my, I have a video on the shooting method for the infinite square well, and I'll put it down below. The nice thing about the shooting method here too is it doesn't have to be V equals 0. It can be any potential because it's just a numerical calculation. We're just calculating it, right? So you can use the shooting method to solve these problems. It's really great. Now, let's look back at the hydrogen atom. We're going to do this for the hydrogen atom right there. That's that equation that we had. Nothing new there. I'm going to start with R is equal to 1. And then I'm going to set an energy of negative 15. And you could guess, but you know where the energy is supposed to be, right? You know what it's supposed to be. Negative 13.6 electron volts. You know that. Okay. So I'm starting at negative 15, just so we can have somewhere to start. If you weren't sure, you can start playing around with it. It's not a big deal. My boundary conditions are at R equals infinity, my potential is 0. And I'm not going to run this to infinity. I'm going to run it to something almost infinity, which is 2. So really what I'm doing is saying far enough away, I'm going to force that to be 0. That's what I'm looking for, that to be 0. I do need to pick my first derivative, right? Because I need to update that. So I need something to start with. So let's just pick 1. Now we do need units. I learned everything about units in quantum mechanics from my buddy Andy Rundquist. So thank you. Shout out. And here we're going to use the units. I normally just use, say, h bar is 1. But if we want to do the hydrogen atom, we want it to work right, then we can use h bar in units of electron volts times nanometers. So it's 197. R is in nanometers. And we're going to start. We can't start at 0, right? Because our function has a 1 over r. And if you put in 0, computers just don't like that. Then we have the Ke squared term for the potential energy, and then we have our mass in mc squared, and so this will all work. Okay, let's do this. Now, I don't know if you know my philosophy for Python, but I'm a simple person. I don't like to use complicated modules or fancy functions or fancy computational methods or fancy programs like MATLAB or Mathematica. I like to do bare bones stuff. And that means that my code's not pretty, but it's understandable. It's not the most elegant. It's understandable. And that's what I want. I want you to understand what's going on. Okay, so I've already started my Python code a little bit. Here we go right there. I'm using WebVPython because I think it's the best. I will give you a link to this code down below, but you need to work on this yourself too. Okay, so let me just tell you some of the stuff I've already put in here because nothing's major. So I have this first stuff right here. This is just for making a graph. Now, and I'll tell you about this y max and y min in a little bit. Here's all my constants. Just said that. I do have L, right? We have L times L plus 1. So I'm just going to start off with L equals 0. You can change that later. It's not a big deal. Start off with my value of R. Start off with dr. That's my R prime. Okay, I'm calling R prime dr. Why? I like the way it looks. I don't want to type prime, right? And then dr, lowercase r, is my step size. I'm moving in the R direction, so that's like my delta x. And then this just prints my energy. I didn't do anything, see? There's no calculation there. Okay, so next, what are we going to do? We need to move our R value and do the recipe, right? Calculate the second derivative, use that to update the first derivative, use that to update psi or R, and then update lowercase r. That's not too much. I can do that. So let's do that. While R, I don't need this. Let's put that at the end. While R less than 2. The first thing I'm going to do is calculate the second derivative of R. I'm going to call that ddr. Now, I have to use that equation that I typed in. I showed you that equation. And I'm going to make a mistake, so I'm just going to copy what I have before. I hope you're not cheated out by that. But if I don't do that, I have another program up here where I typed it. I don't want to make a mistake, because then I'll be like, where did I make my mistake? And all that stuff. So there's the same thing. You can check that out for yourself. It looks a little bit weird just because I don't know why I put the R right there, but that only divides by R squared and it's multiplied by R, so it's fine. Now I'm going to use that to update dr. That's pretty easy. dr equals dr plus ddr times dr. Ha! And just as a reminder, if you're not familiar with numerical calculations, this is not an algebraic equal sign. This is a make equal to sign. So this says take the value of dr, add that to it, and then make that the new value of dr. So I don't have to worry about psi 1 prime, psi 2 prime, psi 3 prime. I just change psi prime. That's what that does. Now I'm going to change the value of r the same way. R equals r plus dr. Looks funny, I know, but look, that's a derivative, and that's the step size. Now I need to update r. R equals r plus dr. If I don't do that, I'm not going to move on to the next interval, right? And my loop will go on forever, and that's just embarrassing when that happens. After that, I just need to, I'm going to plot the whole function, so I'm going to plot each point. I'm going to go along and plot it. Plotting in WebV Python's trivial easy, f1.plot, r. That's it. Okay, let's run it. Now, you'll notice what happened. I started right here, and it went random, and I put in my code, let me show you my code, I put y max is equal to 1, y min is equal to -1. Let me go back and print my final value of r right here. Print r final equals r. And it's in nanometers, but I gotta have a comma right there. I'm gonna run it. 1.8 times 10 to the 12th. Now do you see why I maxed that out at 1? This blows up. It blows up, okay? It doesn't, it's not a solution. But this number is important, 10 to the 12th. So what if I change my energy value to start with? I'm at negative 15, let's try negative 14. And I run it. It still blows up, but now it's at 10 to the 11th. That's not nearly as blown up as before. So let's just decrease it again to negative 13. Now you see what happens. It blew up in the opposite direction, negative 4 times 10 to the 10th. So now I'm too large, right? I'm negative. So I need to make it, we need to hone in on what that solution could be. So let's try 13.5. And yes, there are better ways to do this. There are more elegant ways to manipulate how to modify your energies until you get it to work. But I like this way because you know what's going on. There's no magic, right? It's just you manipulating the code. Now we're at negative 10 to the negative 10th. We're still too small. So let's do 7.5. I'm splitting the difference. Now it's too high. Let's go back down. So we're at 5.75. So let's do 6.25. You can play around with this as much as you want. Still too high, so I want to go 6. Let's try 6. Too low. Oops, still too low. I didn't change anything. 6.2. Too high. 6.15. Okay, too high. 6.12. Too high. 6.11. Okay. So it's between those. Let's do 1.5. Okay, so we're getting pretty good. Still too low. Let's do 1.3. I think we're good enough, right? I think that's good enough. Well, I think I can do a little bit better. It's too low, so which way? I want to go. I missed which way? That 5? 7. Okay, getting closer. 9. Oh, very close. 8. Okay, I'm going to stop. But I can't stop. 7.5. Okay, that's good enough. So you can see there's my wave function. And I have an energy value, right? Negative 13.6118 and so forth. And you could even do better too, right? One of the things that I have over here is my dr. You can make that smaller. Let's just do that and see what happens. Probably break it. Okay. So it's still not perfect, but you can imagine that it would be perfect. See, we're trying to adjust that energy level and our function flip-flopping back and forth. And as we get closer and closer to the actual energy, it'll eventually get over here. Now, it'll never be the real solution. It'll never go to infinity over here, but that's fine. We only care about this first part right there. So that's that. We did it. We made, we solved for r. Numerically, we have a numerical value for r. If you want, you could go over here and change the value of L. Let's just put L is equal to 2. I don't know why. I just want to change that. And nothing happened. Something bad happened. I'm not sure why. Okay, well, I don't want to mess with it. It should still work. But there you go. That's the shooting method for the hydrogen atom. And we know the energy values for the hydrogen atom. The lowest energy level is negative 13.6, right? So you can try to find the other energy levels by just increasing it and seeing what happens. Is pretty fun. Okay, now one more thing. I do have some homework questions for you. If I switch back over here. Homework. Oops, that's not the homework. That is homework. Okay. So it's not normalized. And I didn't normalize it because it's already a 30-minute video and I didn't want to have to spend time normalizing. But you could normalize it. It's not too hard. Integrate over all values of r star r dr and show that from 0 to infinity, which would be 2, and make it equal to 1. Find the expectation value of r. That's not 2 happens. Try changing L's 1, 2, 3. I did that and it blew up and I'm not sure why. And then try helium. So those are some things you can try. I will put down below my shooting method video for the infinite square well. And what else did I say I was going to give you? I can't remember. Well, if I forget something and you think of something, comment down below and let me know. If you made it to the end of this 30-minute video, then you get a high five and I get a high five. Right there. Okay, so that's that. Later.